Hello and welcome to another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 2, Lesson 10, Modeling with Inequalities. So we've kind of been working through this unit, right? We first had equations and what made equations true, and then eventually we used equations to model particular real-world scenarios, and then we solved those equations using the techniques we had built up. In the last few lessons, we've looked at inequalities, what values make inequalities true, and we've looked at how to solve inequalities using the properties of inequality. Probably the most important of which is that when you multiply or divide both sides of an inequality by a negative number, the inequality symbol switches from a less than to a greater than and vice versa. Today we're going to be looking at some real-world scenarios, and we're going to be looking at important key phrases in English that get translated into inequalities, and then we're going to solve those inequalities. So let's jump right into it with our first modeling problem. Now, one of the things that we are going to probably want a little bit of today is a calculator. I've got my TI Inspire hanging out down here. I'm going to drop it back down there until I need it. Okay, just kind of keep it off the board so it's not getting on our way. But you may want to have your calculator handy as well. You probably could get away with a simple scientific calculator or even the one on your handheld phone, as opposed to what other kind of phone? I don't know, your rotary phone? You probably don't even know what those are. Anyway, so there are many real-world scenarios that can be modeled using inequalities. The key will be to recognize common phrases that get translated into greater than and less than comparisons. So let's take a look at exercise number 1. A school is taking a field trip with 195 students and 10 adults. I feel for those adults. Each bus can hold at most 40 people. That phrase, at most, is very important. School administrators would like to determine the minimum number of buses that are needed. All right, letter A. Using a guess and check method, determine the minimum number of buses that will hold all the students and teachers. Show evidence of your thinking, right? Well, this should be pretty easy for you, so I'd like you to just pause the video now and play around with this and see if you can come up with the minimum number of buses that I'm going to take in order to hold everyone. Don't leave the adults behind, okay? You might want to, but don't do it. Pause the video now. Well, just to establish this, right, we need to bring, there we go. We need to bring 195 plus 10, or 205 people. All right, that's simple enough. So, well, let's see. Each bus can hold 40 people. So let's go with 4 buses, right? If I go with 4 buses, times 40 people, I get 160, right? So that is not big enough, right? 4 buses isn't big enough. All right, let's go with 5, right? If I go with 5 buses times 40 people, that's going to be 200. And that is still obviously not big enough, right? We can't leave the adults behind. It comes close, but it's not quite there, right? So it should be 6. 6 times 40 gives me 240, right? And that gets the job done. That 240 is greater than 205, so it looks like I'll need 6 buses. I could certainly have 7 buses, 8 buses, 9 buses, etc., but the minimum number of buses that I can bring in order to hold absolutely everyone is 6. Even though 5 comes a little bit closer to my 205, I would still have to leave 5 people behind, and I'm not going to do that. Okay. So let's take a look at letter B, where we can actually model this using an inequality. Let n be the number of buses taken on the trip. Write and solve an inequality that models this problem based on n. Okay, well, let's do this together. It's pretty simple, right? If n is the number of buses that are taken on the trip, then because each bus can hold at most 40 people, 40 times n, that's going to be equal to the number of people that can be taken, right? If I take the number of people that a given bus can take, which is 40 at most, and I multiply it by the number of buses, n, that should be the number of people that can be taken. And what I know, right, is that that number of people 40 times n must be greater than or equal to 205. The number of people that can be taken must be greater than or equal to 205. Okay? This is going to be a very easy inequality to solve. But I want to be very clear. This inequality is actually what is modeling what's going on in this problem. To solve it, it's as simple as just dividing each side by 40. Right? Now, since we divided by a positive number, that's not a problem at all. Right? And this will tell me that n is greater than or equal to, well, let's find out. We just need to do 205 divided by 40. And that's going to be n is greater than or equal to 5.125. Now, keep in mind the real question was, what is the minimum number of buses that need to be taken? Now you got to watch out in this situation because you could easily look at this and go, well, 5.125, I'm going to round that down to 5. And yet what we saw up here was that 5 buses was not going to be enough. In fact, because the number of buses must be an integer, right? It's got to be a whole number. Well, then the smallest whole number that still fits into this category is 6. 6 is the minimum number, right? 6 is the minimum number of buses that is still greater than or equal to 5.125. If we could have a fraction of a bus, right, just chop off that bus, well then maybe the smallest would be 5.125, which would be 5 1/8 buses, right? We'd have to have an eighth of a bus to just perfectly hold these number of students. But we can't have that. We have to have a whole number of buses, so 6 is the minimum. And sometimes you have to do some interpretation, right, in terms of real world problems on, well, since the number of buses has to be a whole number, it's got to be 6, it can't be 5, because 5 doesn't make this inequality true. All right, let's keep going. At least and at most. These two phrases, at least and at most, are extremely important, and they will often indicate that a greater than or a less than comparison is being made. Let's take a look at those phrases in exercise number 2. Translate each of the following phrases into an inequality. Do not solve. In other words, I don't need you to solve these. I just want to model what's being said with an inequality. Let's take a look at letter A. When 3 times a number n is increased by 12, the result is at least 32. Okay, so really what we're keying in here is the phrase at least. I think the 3 times a number increased by 12 is easy enough, right? That's 3n plus 12. So how should I translate at least 32? Well, I want you to always just put it in terms of, forget about mathematics. If I said to you, I have at least $32 in my wallet, then what would you say? Well, you'd say, well, okay, the smallest amount you could have is 32, but you could have 32 and anything greater than 32. So at least always will translate into a greater than or equal to. Greater than or equal to. So 3n plus 12 is greater than or equal to 32. All right? At least means that we're starting at this number and we're getting larger, right? Greater than or equal to. In fact, I'd rather say equal to or greater than. You know what I mean? I mean, those are the same things, but it's really like, well, it could be equal to 32 or greater than 32. Now let's take a look at letter B. The sum of 2 consecutive even integers, n and n plus 2, is at most 8. Okay, great. So it's at most 8. Now, if I said that there were at most 8 people in the room, how many people would there be? You could say, well, there could be 8, or there could be 7, or 6, or 5. There couldn't be 9, because at most 8 people, right, would imply that the most you could have is 8. But you could also have less than 8. So the phrase at most translates into less than or equal to. And then this is easy, n plus 2, right? That's the sum, is less than or equal to 8. All right? Those are the two most common phrases that arise in inequality modeling problems. Sometimes the phrases greater than or less than appear, right? And then those are easy, because if you see the phrase greater than, you should use a greater than symbol. And less than, you should use a less than symbol. But at least being greater than or equal to, and at most being less than or equal to, those are a little bit trickier and might require you to think about them a bit. Let's get into some more modeling. Okay, exercise number 3. Find all numbers for which 5 less than half the number is at least 7. Set up an inequality that models the situation and solve it to find all numbers. Okay, this is cool. So there's a bunch of numbers that are going to satisfy this. And let's make sure we have it. For which 5 less than half the number is at least 7. Well, let's just worry about the 5 less than half a number, right? 5 less than half a number should be modeled as, let me get back up here, 1/2 n, that's 1/2 a number, and 5 less than it. And that's at least 7. At least is greater than or equal to 7. So that inequality models the information given. 5 less than 1/2 of a number is at least 7, greater than or equal to 7. Pause the video now and go ahead and solve that inequality. All right, well, this one's easy. There's none of those little unfortunate pieces with like dividing or multiplying by a negative. I'm just going to add a 5 to both sides. And I'll get 1/2 n is greater than or equal to 12. Okay, and now I can multiply both sides by 2 to get rid of the 1/2. And I'll get n is greater than or equal to 24. Now again, it's kind of cool to interpret that, right? I'm saying that if you pick any number that's either equal to 24 or larger than 24, that when you find half of it and you take 5 off, you will be at least equal to 7. Right? You know, you'll be 7 or bigger. So like if I grabbed a number like, let's say 30, right? 30 is certainly greater than or equal to 24. If I did half of 30, I'd get 15. And if I did 15 minus 5, I'd get 10. And 10 is certainly at least 7, right? Right? It's bigger than 7. So let's take a look at exercise number 4. When the number 24 is decreased by 3 times a number, the result is at most 9. Set up an inequality that models this situation and solve it to find all numbers that fit this description. Okay, this one's a little bit trickier than the last one, which is of course why I'm going to have you do it on your own, and then we're going to go over it together. Pause the video now and see what you can make of this problem. Okay, this is critical. When the number 24 is decreased by 3 times a number. So I've taken 24 and I'm decreasing it by 3 times a number. So absolutely critical that we start with this, 24 minus 3n, right? That is 24 that's being decreased by 3 times a number, right? The result is at most 9, which means the biggest it can be is 9 and it can be less than 9. So that's our inequality. 24 minus 3n is less than or equal to 9. Now let's go ahead and solve the inequality. I'm going to do my little business here where I use the commutative property to switch those two around. You don't have to do that, but I like doing it. I'm going to subtract a 24 from both sides. That's going to give me negative 3n is less than or equal to negative 15. And now, watch out, I have to divide both sides by a negative 3, which is going to force me to flip that inequality, and I'll find n is greater than or equal to 5. Meaning that any number from 5 and above fits this description. right? So if I took 6, 7, 8, 9, 10, or even the number 5, and I put it into this description, I would find that if I take 24 and I decrease it by 3 times that number, the result will be at most equal to 9. Okay, let's now get into some that are a little bit more, I guess, realistic or real world or what have you. Let's take a look at number 5. A stadium is steadily filling up with people. It holds at most, that's an important phrase, it holds at most 2,500 people. Of the 2,500 seats, 350 are reserved for special guests. When the doors open, people fill the seats at a rate of 10 seats per minute. If M represents the number of minutes that have gone by, fill out the following chart for how many seats have either been taken or are reserved. Okay, so nothing to do with inequalities really at this point. I'm just trying to figure out the sum total of both the seats that have been filled and the seats that have been reserved. And eventually, not yet, we'll have to take into account the fact that at most 2,500 people can be there. So let's do the first couple together and then see what we have. Like after 1 minute, how many seats are filled? Well, after 1 minute, they're coming in at 10 seats per minute, or 10 people per minute. I just cannot get rid of that. Anyway, 10 people per minute times 1 minute, so 10 seats have been filled. The seats that are reserved are 350, so my total is 360, right? After 5 minutes, what would we have? Well, we'd have 10 seats per minute times 5 minutes, which would be 50. 50 plus 350 gives me 400. Okay? So what I'd like you to do is figure out, right, what the total is after 50 minutes and after 100 minutes. Pause the video now and go ahead and do that. All right, well, if you had to use your calculator on this, that's fine. I think I can still do a few more without my calculator. After 50 minutes, 10 people per minute are coming in, times 50 minutes. That means 500 people have walked through the door. 500 plus 350 is 850. After 100 minutes, I've got 10 people per minute, times 100 minutes gives me 1,000 people. 1,000 plus 350 is 1,350. All right. What I'm doing in letter A is I'm just getting a feel for the problem, right? I'm just trying to understand how the inequality might work out in this problem. Let's take a look at letter B. Write an expression that calculates the number of seats filled and reserved in terms of the minutes M that have passed. Okay, real important on letter B. I am looking for an expression. I'm not looking for an equation. I'm not looking for an inequality. I'm just looking for an expression for the total number of seats that have either been filled or reserved. I want to put those two together. Pause the video now and see if you can use what we did in letter A to give me an expression that will calculate that amount. All right, well, what did we do each time? Each time we took the rate, which was 10 seats per minute, and we multiplied it by the number of minutes. That's how many seats have been filled, plus the 350 gives me the total, right? And that's what I did each and every time in that table. I took my rate, which was 10 seats per minute, and multiplied by how many minutes. I then added the 350. All right, let's take a look at letter C. Write an inequality that models all times in terms of all times in terms of M for when the stadium could be filling. Solve the inequality. Well, finally we've got an inequality, right? And what do we know? It holds at most 2,500 people, right? At most 2,500 people. So my inequality has got to be 10M plus 350 is less than or equal to 2,500. All right, 10M plus 350 is less than or equal to 2,500. Now I can solve this. It's not too bad, right? I'm just gonna Subtract a 350 from both sides. I didn't give you a lot of room here to do this. My apologies. Then I'll get 10m is less than or equal to 2,150. I'll divide both sides by 10. I don't need to do anything with switching the inequality symbol. And I'll get m is less than or equal to 215. Ooh, just barely got it in there. M is less than 215. Less than or equal to, sorry, 215. Okay. Let's take a look at letter D. At the rate that people are entering, will any more people be able to find a seat after 4 hours? Justify your yes/no answer. All right, well, I want you to think about this a little bit. Think about the units involved in the problem. Think about what this answer tells you, and see if you can figure out after 4 hours whether or not additional people will be still coming in. Pause the video now. All right, well, we know that people are going to be entering for any value of minutes that are less than or equal to 214. So the real question is, how many minutes does 4 hours represent? So easy enough to just say, well, 4 hours times 60 minutes per hour will give us 240 minutes, right? So that's how many minutes 4 hours represents. But people will only be filling this thing up for times that are less than or equal to 215 minutes. So the answer is no. And because 240 is greater than 215. All right. Let's take a look at one last piece of this problem, letter E. To cover the costs, organizers must raise at least $39,000 from ticket sales. They sell tickets at $25 each. Let n represent the number of tickets sold. Write and solve an inequality that represents all values of n that guarantee the organizers will cover their ticket sales. All right. Well, what I'd like you to do is pause the video now and see if you can solve this problem. All right, well, first we have to talk about how much money you raise. Well, if I take the ticket price, which is $25, and I multiply it by the number of people, which is n, that's got to be greater than or equal to $39,000. I have to make at least $39,000. So I simply write down the inequality, 25 times n must be greater than or equal to 39,000, right? I must make at least $39,000. Okay, now solving this inequality is going to be a piece of cake, right? All I have to do is divide both sides by 25. Since I'm not dividing by a negative, there's no issue in terms of the direction of the inequality symbol. I'm going to use my calculator, I think, to do this one. We could do it the old-fashioned way, but I don't want to take that much time. And I'll find that n must be greater than or equal to 1,560 people. Move my little calculator back out of the way. All right, simple enough. Let's go with one more problem, one more inequality. This is like the last problem of the unit. Exercise number 6. Francisco is on the 21st floor, which is located 294 feet above the ground floor of his apartment. He starts walking down the stairs. Each stair is 0.75 feet tall. Francisco would like to know the number of stairs he can walk down, n, so that he is still more than 100 feet above the ground. Set up an inequality that models the information in this problem and solve it. Okay. So this is a little bit tricky, especially because Francisco is walking down, and we want to know, what is, the number of steps he can walk down so that he is still above 100 feet above the ground floor, more than 100 feet above the ground floor. I'd like you to pause the video right now and see if you can model the information given as an inequality. All right, well first let's think a little bit about how far Francisco has walked down, right? So how far has he walked down? Well, if you take 0.75 feet per stair and you multiply it by the number of stairs that he walks down, that's how far Francisco has walked down. So if I told you he walked down 35 steps, you could do 0.75 times 35, and that would tell you how far he's walked down. It wouldn't tell you how far above the ground he is though, right? To do that, what I want to do is I want to take where he started, which is 294 feet above the ground, and I want to subtract how far he's walked down, right? So that expression actually tells me, based on the number of steps that he's gone down, how far he is above the ground. He started at 294 feet above the ground, and every step that he walks down, he loses 3/4 of a foot, right? It's 0.75 feet. Now I want to know, how many steps he can walk down and still be more than 100 feet above the ground. So I want this to be greater than 100. And that inequality models all the information in this problem. Now solving the inequality, that's another thing entirely, right? This time I think I'm going to skip flip-flopping the inequality around. I'm just going to subtract a 294 from both sides. That's going to leave me with negative 0.75n is greater than negative 194. And now I'm going to divide both sides by negative 0.75, negative 0.75. Immediately I'm going to switch my inequality symbol and also bring my calculator out. And I'm going to do negative 194 divided by negative 0.75. And I'm going to get n is less than 258.6 repeated. I know it says 0.667 on my calculator, but that's simply because I have my decimals set to just 3 decimal places. And so that's the solution to my inequality. But there's this final little part of the problem. Let's take a look at that. What is the greatest number of stairs Francisco can walk down and still be more than 100 feet above the ground? All right, so what is the greatest number of steps that he can walk down and still be above 100 feet above the ground? All right, pause the video now, right, and think about this for a moment. All right, it's a little tricky, right? This says as long as he's gone less than 258.6 repeated stairs down, right, then he will still be more than 100 feet above the ground. Okay, maybe there's something he can see when he's 100 feet above the ground. I don't know, right? So a lot of students might look at this and go, oh, 259, right? Because 258.6, when I round it, that would be 259. The problem is 259 does not fit in this inequality because 259 is not less than 258.6. So in fact, right, the greatest whole number of steps that still makes this true is 258. This is the greatest, and of course the steps have to be in whole numbers, the greatest whole number of steps that still makes the inequality true, right? I think we can all agree that he can only walk in whole numbers of steps, right? So if he walked 1 step, he'd still be above 100 feet, 2 steps, still above 100 feet. He's going down every step he takes, right? Every move he makes, he's going down, right? But he gets into that 257, he's still above 100 feet. 258, still above 100 feet. 259, nope. Now it doesn't fit that inequality and he's dropped below 100 feet. So 258 is the largest number of whole steps where he'll still be above 100 feet. All right, let's wrap this up. So Inequalities are critical in a lot of parts of math. There's a lot of times when we're not concerned with when something is equal to something else, but when we're concerned with when it's at most something else, or at least something else, or greater than something, or less than something. All right, and you'll be exposed to a lot of those in the homework. You've done some of this modeling in past math courses, but of course it gets a little bit trickier now. The wording gets trickier, the physical scenarios get trickier, so you'll get a lot of practice on the homework with it. I want to thank you for joining me for another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.